Hello, hey, I'm Yuan Yu again. So I'm going to give the first talk about the system. So just like what Chengdu said, and I really want this thing to be very interactive. And if you have any question, and please ask me. And also this is the first part is probably the most boring part of all the sessions. And so this is basically the very, very basic stuff. And so I'm trying to get through this as fast as possible. So therefore we can get to the more fancy and exciting stuff. So when you see the program running on the cluster. So LINQ is designed to manipulate collections. So to really understand LINQ, we first need to understand the .NET collections. So the .NET collections is a very, very simple abstraction. So that basically is, you can think about it as a sequence of objects, a sequence of elements. And the base type of the thing is called IEnumerable. The IEnumerable is a very, very basic data type. And so we are going to use it a lot. So one nice thing about this IEnumerable is, this collection is very easy to iterate over the elements. And for instance, if you have a collection of strings, and so all you can do, the simplest way to do it is just for each. Every string in the persons, and you just iterate it and then do whatever you want to do with it. So this is how you can interact with collections. So now it's a little bit more about this collection. So this collection is what we call is a generic collection. So it's very similar to the C++ template, but we don't have to really understand all of this. So the only thing we need to understand is, so there is a IEnumerable of t. T is a parameter, type parameter. And if you instantiate with a concrete data type, doubles, that means I have a collection of doubles. And if you define something about your class in the C#, just like C# and Java, so you can define your own class. So if you define your own class and you say IEnumerable of your class, so that's a collection of objects of your class. So this is the basic collection data. That represents a data set. And so this is the basic unit of things we are going to manipulate most of the time. So, and also it's very interesting as most of the .NET collections implement this, what we call IEnumerable interface. So arrays are collections, list is collections, and hash set is collections, stack is collections, and queue is collections, dictionary is collections. This is all provided to you. They are all collections. And so our job for the next few days is to manipulate, to try to operate on collections. So here is a few examples. And for instance, this is the first example. And so I have an array of persons. It's a string. And so if I want to iterate over the persons and print out the name, so I'll just iterate over the name in person, and we print it. So it's very simple. And so here is another example. Suppose I want to compute the sum of a collection of numbers. This one? So the in is a keyword. In is a keyword. Yeah, string is the type. Okay, so persons is array. But it implements IEnumerable. So therefore, anything that is IEnumerable, and we can do this kind of thing. So yeah, so the second example is I have a collection of numbers. I want to compute the sum. So, and you have the numbers here. And what I do is I basically iterate over the numbers and add them to the sum. So it's quite easy to do. But we don't want you to do this kind of things. And there's a better way of doing it. That is the LINQ. And the LINQ is basically a set of operators on collections. And in this case, you have the key is legal or not. And also here you compute some hash of the key. So, here is a LINQ expression that allows you to do some computation. So I'm going to explain this later on. So this is the kind of computation or the kind of expressions you are going to write in the next 2 days. And so this is the kind of computation. It will ship it to the cluster. So let's first give you a very, very basic summary of the LINQ operators. So the input is a collection. And so the first type of operators, we call it where. So that is a filter. So that means we take, that's the input collections, we only return a subset of the collection, the elements in the collection, based on some condition. And another operator is select. Select operator basically is take where every element in the collection does a transformation and returns another element, return a different element. And so another type of operator, we call it GroupBy, that takes all the elements in the collection and group them based on some keys. So all the elements with the same key would be grouped together to form a group. So here. And also we have another type of operator we call order by. So order by is essentially sorting, right? So you take all the elements in the collection, there is some kind of a compare function on the elements, and so we want to sort it either ascendingly or descendingly. So that's the order by operator. And also we have another operator called aggregate. So aggregate means we take all the elements in the collection, we aggregate them into a single value. And of course, there's something called join. Join basic means we take two collections and put them together and to form a new collection based on some criteria. So for the rest of the talk, I'm going to explain all these operators in a little bit of detail. And so please interrupt me anytime you have any questions. I mean, those operators, we need to understand those operators, so therefore we can understand how they're going to be executed on the cluster. So before I can explain all the operators, and let me first introduce something called Lambda Expression. So Lambda Expression is just a nice way to represent anonymous functions. So here is, I'm giving you some examples here. So this is increment by 1 function, right? So if inc of 10 will be equal to 11, inc of 15 will be equal to 16. So this is basically so this is a way to represent a function without a name. So I don't have a name. So I mean, this is just a function. In the functional language literature, this is called a lambda expressions. And here, so this is so this is basically I say, hey, this is a function from integer to integer. And here, so a second example is a function so that from an integer to a double. So what the function does is to from an integer to compute the square root of the integer. So that's a function. And so another function is that takes 2 arguments. Both arguments are integers and return another integer. So it's a multiplication. So that takes x and y, they're 2 integers, and we multiply them. So this is how we represent functions. And here I don't need to give a name. And I write as a Lambda expression. And so this is the thing we are going to use quite a bit for the when we get to the writing of the programs. So this thing is very similar to the, if you know the C++ function pointer. So this is pretty much is a function pointer, but that's not very important. So now let's get to the operators. The first one is where operator. Where basically filters the elements in a collection based on a predicate. You know, we only keep the elements that satisfy the predicate. So, and here is the signature of the function. So I'm taking a collection. So that's IEnumerable of t. So that's my collection. That's my initial collection. And so the second argument is a predicate. That means it's a function from the t. That's my element type to Boolean. Okay. So operationally speaking, what happened is I'm going to iterate over the elements in the source and only keep the one that satisfy this predicate. So as an example is, say for instance, this is how we write LINQ expressions. So we have some array. So that's a collection of integers. And what I write is a dot where, applying the where to a. So a is our source, and applying this predicate as x greater than 4. So the result would be 5, 12, and 5. Yes.
So if the function returns a false, then what happens?
The element is dropped.
So it's
Okay.
a
So
situation where if it's true, do this, and if it's false, do
no.
something else.
So basically, it returns a sub collection. That means all the elements in the sub collection satisfies the predicate. Yeah. Sure, I can give you a copy of the slide. But there's a lot of materials about LINQ on the internet, but of course I can give you this. I can make the slides available too. So the second operator is yes.
Is there any restriction on the actual function is being passed to where? I mean, the level of recursion or anything, or it's just a normal function?
It's just a normal function.
I mean, the reason I'm asking is that if there is a lot of recursion in the false stack class, so iterating the where.
Where you can write as a simple loop, so there is no recursion in where. Okay. So imagine what happened is you can just for each x in A, and if the predicate is true, and return the element. If the predicate is false, just do nothing. Yes.
Suppose there is a function that I need where I need more than one element from that collection.
More than one element in the collection?
And they have to go on like some I plus 1. So it takes like any element and some of the next element has to release that has to be out.
So say again.
So I need an element to shape the collection. And I need that element to operate on 2 or 3 other elements in the same collection. Then it has to go on from one.
Well, so I mean, you're talking about some sort of a kind of a sliding window, right? Yeah. Okay. So this operator is not good for that. Okay. So this is basically it operates on each of the elements independently. So this is where, in fact, this is why this one is highly parallelizable. It's because of you can basically do the computation completely independently in parallel. Okay. So the second operator is select. So that basically transforms each element of a collection into a new form. So if you look at the signature of select, it takes I have a collection, and the element of the collection is of type T, right? And I want to return another collection, and the element of the collection is of type R. So by applying this function takes an element of T and returns an element of R. So that's for each individual element of the collection, I apply this transformation function, and that returns us another collection. And so here is a very simple example. And what I do is I have a collection of integers, and now I'm going to apply this operator, and with I want to square every element in this collection. So this is how I write it.
You don't have to specify the data here.
You mean here? This is a typo, I'm sorry. So that should be int.
So what does that mean?
Select means you apply a transformation to each element in the collection.
Doesn't it sound little counterintuitive? Select is supposed to select something from transform would have been a better. Map is the standard name for such function.
Yes.
The historical reason for why it says that SQL select, because they select a column from a record. Just a simple form of applying the function to the record. The function that pulls out of that column. The more general form of select is do whatever you want with the record.
Right.
Sort of,
Yeah.
the legacy of it.
Yeah.
So this essentially means that select is kind of an iterator. You just make a function on how it is. It's map.
It's a map.
That's absolutely not with the name.
Yeah.
More familiar to SQL.
So all the operators come from the SQL background. And so select another way of calling select is projection. So typically people call it a projection operator. Yeah. But here is a generalized version of the projection.
For these functions, what we define here as lambda expressions, can they be defined earlier and used?
Sure, you can define some earlier, and so you can say, for instance, you can define a multiply function, and then here you just call the multiply function. Right. So, but lambda expression is a very convenient way of writing anonymous functions. Oh, you're here, right? So that is really not necessary. You can get rid of this part. Okay. So it's yeah. So, and now I showed you two operators, where and select. So the interesting thing is, if you look at the signatures of the operators, is take a collection and return another collection. So that means you can easily compose the operators. And for instance, what you can do is you can have, so I have an initial collection, a collection of integers, and first I apply the where operator. And so that give us back another collection of integers. And I can subsequently apply the select operator. And so that gives us another collection of integers. And so this set of operators is very nice in a way. So you can just, because of it operates on collections and returns collections, so you can just compose them. And or you can simply write, the collection.where and .select. And sometimes you find as two. Yes.
When you do the select operation, what is the order in which the results are stored? Like here we are doing the select on the set 1, 5, 2. So the result should be 1 square, 5 square.
Which one? This one?
Yeah. R1 dot select.
R1.select. Okay, so we apply the where operator on A, and so that gives us R1, which is another collection. And now from R1, I'm applying another operation, and that gives us R2.
Is there any particular order in which elements are stored? Like here, it would do the square operation on the elements 4, 5, and 12.
4.
5.
That's a very, very good question. So the semantics of LINQ, this is not specified in the semantics of LINQ. So because of this, and we can do, say for instance, parallel processing of each element independently, and we can return them in arbitrary order.
In the second example, what's in that?
You mean which one? This one?
That IEnumerable T.
Yeah, so this is another typo. That should be int. That should be int. Yeah.
Again, in the previous slide.
Yes, that's exactly the same thing. So that should be int. Yeah. So T is a type parameter, and so it shouldn't occur in your program. Most of the time, it shouldn't occur unless you want to define a generic function. So
What now specify for T?
the
Specify anything like in the first example. If I don't specify the IIT for R2, what will it take that as?
if I don't specify this, it's going to be a compiler error. So and also, and as you know, writing this kind of thing is kind of a little bit of tedious. You know, I make mistakes here. So and in C# we introduce something called var. So that can be you can write it, what you can write var in replace of this IEnumerable of T or IEnumerable of int. Okay, so that's just a shorthand way of writing the type of the variable, and but the compiler would actually do static type inference, and internally the compiler actually knows what the type of this variable is statically.
This is something like SQL query.
It's similar, but you'll see the difference soon. So, and also if you really don't hate this lambda expression, so I'm not recommending you using this SQL-like syntax, but if you really hate lambda expressions, you can write things without this lambda expression. So for instance, you can write it in this kind of SQL-like syntax that so this is your collection, and you say from x in A, and where x is greater than 4, and select x times x. So this is just alternative syntax, and you can use to write your programs. And one interesting thing about LINQ is you have user-defined functions all over the places. And for instance, I can in the where operator, I can define something called my predicate, which my predicate can be defined in a library or somewhere in user code, and so this is the place that is different from SQL. That is, in SQL, it's hard to define user-defined function, but here is the user-defined functions are the C# programs are seamlessly integrated into the operator, so that allows you to basically call any functions in your program. So this is actually the place that is very, very different from SQL. For instance, here you can do select. You can call the math library, the square root of x. So it's very easy to use user-defined function for the.
What do you mean by that again?
You mean it here? So my predicate is some user-defined code. It can be is your code, right? You can write the predicate. You can write the method. You already define, just like you define a method and you define a function, and you want to use it. but you can use it in the where operator. Okay. So,
the return type should be bool.
So this one returns bool. It's a boolean. It returns boolean.
Is it always bool or can we define anything else?
So remember the signature of where. So it requires you to have a lambda expression, right? So that takes takes the argument of type t to boolean. So this is the it has to return boolean.
When you say these statements are parallelized, these are internally parallelized or?
So on my part of the talk, and so I only tell you the semantics, or I'm only introduce you the operators, and so in the subsequent talks, and we'll tell you how those operators are actually implemented in dry LINQ, and map it to dry it for execution.
Does the where operator necessarily reduce the dimensionality of the function, right?
No, I mean it works on anything which is, I call it IEnumerable. So any collection, and I can apply this where operator.
So does that when I use that my predicate, can I have it? Can I force it to preserve the length of that where?
Oh, unfortunately, no. When you talk about IEnumerable, and sometimes the length is not important anymore. So we're talking about the collection, and so the collection, you can enumerate the elements in the collection, but also you can compute the length, but the length is a variable. And in fact, anytime when you apply where, so you return something which is it may not be an array anymore. It's some internal representation of some collection.
Is there any description that where should return a collection of the same type as the original collection?
It's where has to return this. The element type should be exactly the same.
Because here it's returning bool, and the original collection is of type.
So where returns, if you go back to here, so where applies a predicate to every element, and it returns an IEnumerable of t. So you start with IEnumerable of t. You start a collection of type t, and you return a collection of type t. So So basically what happens is all the elements that satisfy this predicate would be in here, and all the elements who, It's a filtering operator. So the next operator is a little bit more, hello?
We used the var expression to get the results, right?
Yeah.
Can we use the same thing, to define any data set? We defined basically an array of integers initially.
Yeah.
And then we took the result, which is actually maybe an array or maybe an element.
It's IEnumerable of integers.
Yeah. So
yes.
Can we use the same var expression to define anything we want?
You cannot use the var. You can use var to define everything you want, right?
So I can say var a and then.
Oh, that part is no, because at that time, you don't know what the type of A is. So A is when you declare A, when you introduce A, and you have to write. So I mean now the select many is a slightly more complicated operator. So what it does is to take every element in the collection and transform every element in the collection into an IEnumerable, and then flattens the resulting sequences into one sequence. Okay, so it's a little bit complicated, but let's take a look at it. So what select many does is you take your input source, which is a collection of type T, And now you take another function. So this is similar to select. But the difference here is takes one element and it generates multiple elements of R. Not only one, but multiple elements. It generates a collection of R. And then what it does, the select many operator does, is to take all the multiple elements and flatten them into a single collection of R. So let's take a look at a very simple example. So say for instance I have two lines, right? So this is IEnumerable. That's a collection. The collection has two lines, right? So when I apply select many to the lines, and what I want to do is I want to take a line and split the line into words. Okay? So that means for each line, I return a collection of words. And what the select many does is to have, for each line, it returns a collection of words. And what the select many does is to flatten all the collection of words into a single collection of words. So in other words, the result of this operation would be a line of words of wisdom, right? So we return the words, and it's a collection of words, and then it's dryad and dryad link are great. The R is the return type. Here is the return type is string. Array of two. It may not be array. So internally, we should always think about in terms of collections, right? So what it does is when the first line is applied to this operation, where I have a collection of words, and the second line is when it's applied to this operation, and I have another collection of words, and now I'm flattening the two collection of words to form a single collection of words. Uh-huh. So the select would actually return an IEnumerable of two collections, right? Yeah. I mean, it needs a little bit of practice, and we'll get a lot of practice later. So, but this is actually is very useful and very important to get some kind of rough understanding of all these operators. Yes. No, there is no duplicate elimination. So this is just you keep all the it's sequences here.
What is the difference that a select many is making? You usually have two lines anyways, and select many are two separate lines also.
I'm producing an IEnumerable, a collection that contains all the words in both lines. I'm combining the two lines into one collection, and the collection contains many words, right? So it's going to be a line of words of wisdom, dryad, and right. So that's a flattening operator. So this is a very useful operator. So the next one is actually easy. So that's order by. So order by basically sorts the elements of a sequence in ascending order according to a key. So it takes two arguments. The first argument is a collection. For all these operators, the first argument is always the input collection. So that's a collection we're going to do some kind of operations on. So the second argument is a function that that means for each record, I compute the key. So, and so the key is used to do the sorting. So here is a very simple example. For instance, I have a collection of employees, right? And if I want, and for the employee, I have a field which is the name of the employee. And so if I want to sort based on the name, and I'll just do the employees, apply the order by operator, and sort on this key, which is the name of the employee. Yes?
What if the sorting is, you are assuming that the compiler knows or the runtime system knows the order, sorting order?
That's a very good question. So here, so we are assuming that for this, the name here is, so probably it's a string, right? So we're assuming we know that there's the sorting order of the strings. And here, so we're assuming, so there is a compare function on the key. So the next operator is also very.
Order by what kind of algorithm is used internally and what's the complexity of that compared to regular one?
Well, so that is going to be the topic of the next lecture. And so we'll talk about how to do.
Which complexity is there in it?
It's obviously sorting is n log n, right?
You can sort it by several different ways, but
Yeah.
your order by is the best one.
Oh,
In the best way.
yes, yes. You know how good it is. So the GroupBy operator is a very useful operator. So that's an operator we really want to make sure everyone understands. Okay, so but it also is a little bit more complicated than order by. So what it does is it groups elements of a sequence according to a specified key selector function. So basically, I have a collection of elements. I want to group the elements with all the elements with the same key. I like to form a group for all the elements with the same key. So therefore, the return value is a collection of groups. Okay, so I'm returning a collection of groups. So it's always the case. The first argument is a collection we are going to operate on, and then the second argument is the key selector. So that means I select the key that is going to be used to form the groups. So this I grouping is also is an interface, and it exposes two things. One is this I grouping itself is also a collection. Remember, so that's a group of things. It's a collection, and also if you do g.key, so that gives you the key of this collection. So it's not only a simple collection, it also tells you the key of this collection. So that is what I grouping is. So let's take a quick look at some examples. So suppose I have a collection of integers. I can say numbers.groupBy, and I form the groups based on the remainder of the integers. So that means all the numbers with the same remainder would be in the same group. So it's quite simple. So here is another example, and I have some items, which is some wedges, and but I want to form groups with the first character of the name of the veggie, right? So what I do is I take the items, I do a group by, and so remember, so each element here is a string. I use the first character of the string to form the groups. Okay, so therefore, if you look at the result of this, would have there are how many groups? There are two groups. So the carrots and cabbage, they are the same group, And the broccoli, beans, and the barley, they're in the same. They are not in another group. So another interesting operator is called distinct. So this is the duplicate elimination. So I remember you got a question about whether do we want to keep the duplicates. And so this is the operator that get rid of the duplicates. And say, for instance, if you have a collection of numbers and the numbers that are distinct would basically get rid of all the duplicates and only returning the distinct numbers. And another interesting operator is aggregate. So aggregate is you take the collection and you apply some kind of function and you return a single value. So that's an aggregation function. So this is your collection, the input collection, and you are trying to apply a function on each element in the record. So the R is the current result, partial result. So I'm basically applying a function for every element in the collection and try to compute the final result. So it's very easy to, if you look at a very simple example. So for instance, I have a collection of doubles. If I want to compute the product, so how do I do it? Here's the doubles. I apply this aggregate operator. I supply the seed. The initial value is 1, and and then what I do is this is my partial result, and this is the next number, right? So that the partial result times the next number. So that means I keep multiplying all the numbers one by one. So that gives us the product of the doubles. So
Can we, as she was asking, can we access the different positions? Suppose I want to get the product of the first, third, and fifth numbers.
So the kind of interesting thing here is anytime you get to the index of the individual elements, and it's becoming less parallelizable, right? So the idea is you operate on the whole collection.
But the answer is yes, you can.
Yes, you can do it, but that requires yeah.
So you haven't been saying much about the distinction between sets and sequences.
No, I don't want to get into that part of the work.
And none of you have asked, but for something like distinct, they may not come out in the same order that they went in.
Yes.
He didn't guarantee anything about the ordering of the sequence.
Yeah.
This seems to be the old R function of functional languages. Old R, the old or reduced function.
Yes.
Which combines them.
Right.
Can you go over this example?
Excuse me?
Can you explain this example?
Okay, so you have a collection of doubles, right? But now what I want to do is I want to compute the product. So how do I go about it? And I'm applying the aggregate function to the doubles, and I have an initial seed. Is a partial result. The initial partial result is 1.0. It's a partial result, and R is the current partial result, and N is the next number, right? So and what I do is I have the partial result, and the partial result times the next number. So if I iterate, conceptually the aggregate iterates iterate over all the numbers, right? So multiply them one by one.
How is M always the next number? How do you know that M is the next number?
So that's just the function you give, right? I couldn't hear you.
Sum of squares, first n number.
Summation of squares, say first n numbers.
The first n number and the
Sum of that, sum of square of that.
sum of yes.
Every element.
So
If we initialize to 0, then we need to pass a fixed parameter as 2 and then.
yeah.
I think it
That would be
followed by a select followed by
Yeah, you can do a select. You can do a first probably or take. You get the first 100 elements, and then you do a dot select, and the select is x goes to x times x, and then you can do a sum.
Or you could have done it with aggregate, so it was there and already,
And so the aggregate function is a little bit hard to use sometimes, as you probably saw. And so there are some predefined aggregators for you. So there's a count. So that means you have a collection that counts the number of elements in the collection. And also you can do, so if it is a collection of integers or doubles, and you can do sum, you can do max, you can do mean, and you can compute the average. And also there's something about contains. That means you say whether some element is in this collection or not. So this is all. And so here is a very simple example. And also, so here is a count and also a long count. So the count, it means you can only count the size of the collection can only be 2 to the 31, because of that's the return type of the count is an integer. And the long count is the 64 bits. So I recommend to use long count all the time. So this is, we really don't want to use the count, and so that has a potential of overflow. So now let's get to a few very simple exercise. Keep all the numbers divisible by 5. So this is the code, right? So what I do is for each number is if it's divided by 5, if the remainder is 0, I keep it. Otherwise, I throw them away. So the average value of integer collection. So that's x dot sum divided by x dot count. And normalize the numbers to have a mean value of 0. So how to do this? And so the answer is you first compute the average. And then what you do is you do a select. So that would normalize all the numbers and to have a mean value of 0.
You define the predefined average. Is there a difference in the behavior of this?
That's a good question. So here you can use the built-in average, and also you can do it by yourself. So I'm doing it by myself.
What is the plan? Like you have x dot sum and then the blank type.
You mean this? Parens? Parens means it takes no argument. It doesn't take any argument. So keep each number only once. And we know there are 2 ways of doing it. One is, remember we talked about the distinct operator. So that's how we keep how we generate the collection, with all the duplicates eliminated. And also I can do it the following way. I form a group, right? I form a group. So that means all the same numbers are in the same group. And then what I do is I only select the key of this group. So by doing this, I get all the distinct numbers. So here is a little bit more exercise, flatten lists. So it's very, very useful. That is, select many. So suppose, yes, select many flattens list. You have IEnumerable of IEnumerables. If you want to flatten it, and so you do a select many. So that would flatten it. You flatten only one level. Yeah. Yeah, you have IEnumerable, a collection of collections of collections, right? So here is basically you have a collection of collections, and the select many would flatten one level of collections. So the average of all even numbers and all odd numbers. So what I do is I form two groups. So all the even number groups, the even number group and the odd number group. And for each group, I compute the sum and divide by the count. At the most frequent value, so this is a little bit more complicated. So what it does is, so I want to compute the most frequent occurring value in a collection. So what I do is first I do a group by, so that now all the same numbers are in the same group, and then I order by the size of the group. So that means now is the largest size of the group with the largest count would be ordered first. And then I select the key, so that's the largest, that's going to be the value, and I choose the first one. So that gives us the most frequent occurring value. So the number of distinct positive numbers, positive values. So first I do a filter here. So that gives us all the positive numbers. And I do a distinct. So that gives us, get rid of all the duplicates. And I do a count. That gives us all the, yes?
So you mentioned that actually indexing is not an order of elements. Is not part of the abstraction.
Yes.
It's actually opening to the abstraction. But the moment you do things like first, you seem like you're breaking it.
Yeah, but yes, and also this, you are absolutely right, and also this one is really bad. Yeah. 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 And basically what happened is, anytime order by introduce ordering. Okay, so there's if you care, so there's IEnumerable, there's IOrdered enumerable. And anytime when it is being ordered, so the ordering would be preserved in the subsequent computation.
Another way, I don't know if this is helpful, if you don't ever want to rely on the ordering because you don't just do one, you could certainly write things like the group by that gets to account, and say dot match, and say, well, how frequent is most frequent whatever happens. And then do the same thing again, if you're aware that only key people will frequently use whatever the match is. Particularly giving a set of values that are most frequent.
You could do the bad part, saying top everything that's greater that's less than count, and that would be kind of order.
Okay. Yes.
Just out of curiosity, there are multiple ways of finding, say, a distinct element.
Yeah.
So, out of curiosity, I'm asking, which would be the better way to do it? Say, considering my data set is like, say, some 300 million nodes.
Just apply distinct. Distinct would actually do a very good job. And the other way of doing it is also doing a very good job. So there's not much difference. But distinct is a built-in operator, and also you can use it directly.
My understanding is that if you're using two operations, you're traversing through the list twice. Or maybe a bigger list and then a smaller list. Right?
No.
Something like that.
Yeah.
Internally, distinct is doing something similar, they're doing the same.
Just to make a high level point, which I don't know if you want to remember, one of the really nice things about doing all these things declaratively in some sense is that you're asking the system to go and figure out, you do this the best way you know how. I could have specified a bunch of loops to review, but instead I'm going to relinquish some control to let the system reflect on where the distinctive account of the system will run something like this all at once. It will run through one single pass, as opposed to having relied on multiple steps to actually take. So it's why these operators look sort of vague and underspecified, but it's actually very powerful.
Okay, so here is a little bit more elaborate example. So I think this is basically what it does is to compute. What is computing? So, that's a good question. What is computing? Okay, it computes the most frequent occurring words in a document. So imagine, the input is a collection of lines of some novels or some texts. And what it does, the first thing it does, remember we talked about this, is to split the line into words. And so therefore we get, and then flatten it. So now I have a collection of words. That's a collection of the collection of words of the entire document. And then I'm doing a group by on the words, and forming a group for each word. We form a group, and then what I'm going to do is for each group I compute the number of words in that group, so that gives me a count how the popularity of this particular word, and then I sort it based on the count. So that gives us a descending order of with the most frequent word in the head. So and then what I do is I take K, so that's the top K most popular words. So this is the answer. So so for instance here is so this is your initial input, and by applying the select many, give you basically a collection of words. And by applying the group by, that give you groups. And then applying the select, that give you the counts, the number of words in each group. And then applying the sorting, and we get off. There's two occurrences of off, and one occurrence of A, and one occurrence of line. And so, and if the K is 3, the top 3, so that gives us the off, A, and the line. So this is the kind of program people actually write. And in the next lecture, Michael is going to tell you how this program is going to be transformed into dry computation and running on cluster with, say, for instance, terabytes of data as the input. So, and another thing is, this is my final slide, is if everyone heard about MapReduce, and this is how MapReduce is expressed in LINQ. So this is here is your mapper. Mapper is, as people observed, the select is map, essentially map. So you take a map function, so that's basically applying the select many on the map function. And then you do a grouping based on some key, and then you apply your reducer. So this is your reduce function. There's map and reduce, and with the shuffling phase in the middle. So this is what we call it MapReduce. So that's pretty much conclude my talk. So, and any questions? So by doing this, I hope you get some kind of understanding about the operators. And I believe the first thing we want to do is to do a little bit of, when we get to the lab section, and we'll do a little bit of work on writing your first LINQ program and writing your first dry LINQ program, and do a little bit of a practice of using those operators.